Let me just move this anyway. Nope. All right. Okay. There you go.
Yeah, thank you very much for the opportunity to present my work here. I'll talk about joint deconvolution of astronomical images with Poisson noise. I can take one part already away, and this is you will not see a lot of deep learning here, but you'll see a lot of reasons why you might think twice, for example, why to use deep learning. And here's one use case where I ended up what I would call like a machine learning or deep learning inspired method. So this is the X-ray and gamma ray sky. So this is the sky measured by the Fermi LAT instrument. This is the sky measured by ROSA. So there are many scientific questions related to interest things. So we're just taking a look at active galactic nuclei with Fermi LAT. There's a lot of emission in the galactic plane. There's, for example, the structure of the Fermi LAT bubbles here, Fermi bubbles. But as you can see already now, in the galactic plane, there's a very, very high source density. So problems like source confusion are already very much present. And a lot of the knowledge that we can gain is already limited by the angular resolution of the instrument. Similar situation a bit for the X-ray sky. There are also like a lot of structures. There are global structures, but also like very local structures. And we're interested in things like morphological details, or for example, supernova remnants and these kind of things. What's important here is that the brightness and fluxes that we're looking at, X-ray and gamma ray energies, are really low. So we're observing the universe at this range basically by counting photo events. So we're looking for single events. The signal to noise ratio is really, really low. And to get a good signal, it also requires very long exposure times. So this is a simplified version of how we take those images. So this is what I call like the low count imaging process. So there's some true underlying flux distribution. This is how the universe or the sky actually looks like, but we can only use that for our instrument. So this instrument has a limited angular resolution. This is typically quantified by the point spread function. This means what we actually see is something, a blurred version of this original thing. Then, in addition, we have non-uniform exposure. So the instrument, for example, like Chandra, will point to the sky at a certain for a certain amount of time, and then you have to combine all these exposures to a single image. But it's very non-uniform. So you have these overlapping structures. We have high exposure and non-uniform to correct the image. And then, if you really count photon events, then what you end up is a lot of photon noise or Poisson noise, and your final data actually looks like this. So you come from this, what you're actually interested in, to what we actually observe in the data. And the question is now whether we can reverse this process. This is known as the classical statistical treatment. It's called the unblind joint or the unblind deconvolution problem. So we have this observation here of the sky. Possibly we have, for example, multiple observations. So it would be interesting for us to know that we can actually combine the data. This is typically done, for example, for Chandra data just by stacking the images. So just summing up all the counts across multiple observations.
So you call it unblind because you assume that you know precisely the PSF and the exposure.
Exactly. So this is
the
part here.
And so when you actually know those?
That's an important question.
Okay.
But the assumption here is that you have some estimate of what the PSF and the exposure actually looks like. Typically, the PSF, for example, can be either simulated, so you have some model of the instrument and you can simulate it, or you get it empirically from data, such as like observations of AGS. But the assumption is that you have some more knowledge on the problem, or some more prior knowledge, so you roughly know what the PSF looks like and what the exposure looks like. And then the hope is that you can somehow reconstruct this single flux image. So why not just use end-to-end deep learning for this, right? I mean, this looks like a classical problem that you could just say, okay, we'll solve it with data, and we'll solve it with deep learning, machine learning. Here are some problems with this. So in general, I think there's a lack of training data, right? So astronomical images are expensive in time, so you require long exposures, and they're also like financially expensive. There is no ground truth, so we don't know what the sky really looks like. we only have the data that is observed, and this is distorted by all instruments. So there's just no ground truth to learn on. Also, the gamma ray and X-ray data is sparse, so there's just like not much of it, and the signal to noise ratio is really low. And ideally, as I said, it would be great to have the possibility to combine the observations, and this is not obvious how to do this with machine learning. Then I've also looked into one specific argument. So you can actually show that, for example, small deep architectures are actually not suited for the deconvolution task. You can make a very simple argument for that, which basically just goes through the Fourier space. So you can show that to require or to actually solve this problem, you require really large kernels or very deep architectures. And this works if you have a lot of data. But this is also just not lucky in our case. In addition, and I think this is probably more important thing, is also that Poisson data is always in the low signal to noise regime. So we're interested in specifying the type 1 errors. So we're interested in getting something like a false detection rate or false detection estimate of, for example, a feature or a source that we have in the image. And for this, it's nice to have a full specification of the likelihood. And this is not possible with all deep learning architectures, only with some of them, like normalizing flows, for example. There's one last argument, and this is, there's a lot of prior information, for example, the Poisson statistics and the data, for example, the shape of the PSF and the exposure, that you would need to learn. And it's unclear how to put this in as prior information if you just do something like machine learning. However, something like transfer learning or simulating training data, this could work. And this is just a very fair approach. So what I've chosen in my case is a more classical forward folding approach or forward folding modeling approach. This, I think, is more common in X-ray and gamma ray astronomy with some elements from machine learning, where it made sense. So here's a little bit of math. We can actually compute the likelihood for a given observation just by assuming there's Poisson statistics per pixel. Then you sum up across all pixels, so you have the actual data, this is E, and then you have the expected number of counts, which is the lambda here. You compute the Poisson likelihood, then you sum it up, take the negative log likelihood, and then you could just say each pixel in an image is an independent parameter, and you just optimize for it. That's like the naive thing to do. This has been solved already a long time ago. So there is a solution to this using expectation maximization by Richardson-Lucy, and you end up with some structure or some updating rule for the starting image, and then you can show that this actually converges at some point. So you start from some image, and then you get an update, and once you run this for long enough, then this actually converges. The predicted counts here are given by the true flux. This is what I call the X here, and then you just forward fold this with the PSF. And this model is known. However, there's a problem with this solution. So this I've just illustrated here. And so this uses this classical Richardson-Lucy deconvolution. Here's just some simulated data from my face. So this is the gamma ray selfie of myself. What people have done, or you can see what's happening. So this is the reconstruction, just doing one iteration for Richardson-Lucy. Here doing 10 iterations, 100 and 1,000. And what you can see is that actually the structures, or what are correlated structures in the image, they start to decompose. So this actually decomposes into a set of point sources, some density, whatever. And what's important about this is that after you take the reconstruction and come up with the PSF again, actually the reconstructions look very similar. So there's, and the same holds true if you compute the residual count. So if you compare this again to the actual counts you have, then this is, you could just for the sake of the argument just say, okay, this is good residuals, the same here. So there's no good way of actually distinguishing between those solutions, because they all show good residuals and model counts, but the reconstructions, as you can see here, are very, very different.
Yeah, but the Fourier spectrum of those are quite different if you look at it. So, and that's the fundamental problem of the convolution. You cannot deconvolve because you cannot divide by 0.
This is the naive solution, right? So you just say, okay, like you can divide by the by the PSF, well, by the
You need to try it
for it.
because you cannot divide by 0.
Yes, I think this is called like Wiener deconvolution. That's typically what we do. But as I said, like the problem is still fundamental, right? Because after the PSF convolution, I mean, those look identical, but those reconstructions here look different. And there's no, and this is what's called just like an ill-closed inference problem, right? And the question is like how to get a better solution for this. And the answer here is that you can use space theorem, so to the rescue. So what you put in, you get more plausible reconstructions. This is what I would call is some prior information. And what you need is prior information somehow on the structures that you have in the image. So here in the lower right is just a very simple example. So we as humans are good at this, I would say. So we've seen a lot of astronomical images. So we can tell this image here is noise. This is an unlikely image. At least if you look somewhere where you expect something. This is probably a more likely image. So there's already some structure. And this is a likely image. So this is what like an astronomical image looks like. So there's something to be learned here. So what we can do is we can extend the log likelihood term just by some prior. The question is which one to choose. And the problem here is again like learning the probability distribution for a full image is really hard. It's a high dimensional learning problem. And again, we're very limited with our data that we have. So there's just not enough data to really learn this. And structures are really diverse as well as. But there's an interesting approach. This is called, or what to call like the patch-based image prior. So this is an idea that actually comes from computer vision, and then was later adapted for reconstruction of radio data. And this was also used, for example, for the HT image. And I think this is actually, I think like a few weeks ago, Bill Freeman talked about the reconstruction using diffusion models as priors. And I think like the prior version of this algorithm used the patch priors. And this is what I've applied for this one as well. So the idea is the following. You take some reference data set with, or reference image with very high signal to noise. For example, this beautiful image of the James Webb Telescope. I've also used GLEAM rate survey data. And I think the exact choice here is not important, except that it's an astronomical image and it has high signal to noise. Then the idea is that you split this into multiple patches. So patch here is defined just as a small rectangular region of the image of the size 8 by 8 pixels. And this gives you some distribution of the local structures that you find in this image. And then the idea is that you just model this using a Gaussian mixture model. In this case, it's 64-dimensional, so like each pixel in the patch corresponds to a single dimension in the Gaussian mixture. And because you're working with these small patches, you can actually extract like multiple millions of those patches from one single image. So this then, and then you can train, for example, using expectation maximization. So the training with algorithms is what we found.
So when Bill was talking, I think one of the things they wanted to show is if we use priors that are black holes, then how can we tell for sure that we're seeing that and it's not just prior dominating? Do you have any? He showed also that for just any images, training it on images, and even on celebrities was not working so well, but in different kind of images also work. Do you think there's something intrinsic to an image that if you didn't use astronomical images would still help to have as priors?
So I'll show some results later, and there I compare against a patch prior that was learned from everyday images. And I see some slight differences. So if I remember correctly, for example, in their publication with the original patch prior, they've shown that their results barely depends on the choice of the prior. I think the assumption here is that locally structures in images are very, very similar. But I think in general, this does not necessarily apply. For example, it's clear that in astronomical images, there are point sources. Those are, for example, not present in everyday images typically. Yeah. But concerning extended or morphological structures or local correlation structures, so things like corners, like edges, I think those are universal to images. And this is also what actually happens then once you train the Gaussian mixture model, those are the means of the Gaussians here, and you can see that those converge to certain image structures. Yeah. So here's an edge. Here's something like a corner with a slight curve. Here's another edge. Here's a diagonal structure. Here's a horizontal one. Here's something peak in the center. I think the exact structure here is not necessarily important. So a Gaussian mixture model has this property of that it can actually approximate any distribution if you just have enough Gaussian mixture components. And this is what you rely on here. So you not necessarily use this as a classification item, but just to represent somehow the prior image. Yeah.
So you've got a bunch of, I guess, 6 or 20 Gaussians or something there.
Yeah.
And you're showing the means. So they each have a covariance, and what are the leading eigenvectors or eigenimages of those covariances? Like for number 3, where you have things kind of at this angle,
yeah.
Are the eigenvectors just sort of other variants of that, or are they totally different? Or
so I don't have a visual representation of the eigenvectors. I can like on the next slide, I can show this. I'll just take this away. So here's just one example. So this is an example image here, and I'm taking a look at this patch here. And these are 3 Gaussian mixture components. And what I'm showing here is just the linear combination of the 5 leading eigenvectors of the covariance matrix. And this is what it looks like. And the intuition here is that this thing basically acts somehow as a denoising algorithm, let's say, or like a denoising version of the actual data patch. So there's, I think in the original publication where this method was proposed in the computer vision field, they're actually showing those eigenvectors and eigenimages. And what they've observed is that they actually seem to converge to similar things, for example, that you see in deep neural nets in the first layers. So you have partly, you have so what does this structure look like? It's the, how to describe this? It looks a bit like wavelets, I think. So you have like a regular pattern, and then
and edge finders. I mean, you're
yes, and edge finders. Yes, yeah.
At different angles. Yeah. Which makes perfect sense.
Yeah.
But then you're basically asserting any patch is some linear combination of these means plus a linear combination of eigenvectors weighted by their squared eigenvalues or whatever.
What I do in the reconstruction is slightly different. I'll explain that on the next slide.
All right, I should let
yes.
you. Okay, sorry.
Yeah. I think there was another question.
It's very common.
Yeah.
Question here. So it's about how do you determine the size of the patch you choose and how to decide how many patches you use. I think you just use different patches to learn something about the noise and the data of the image, right?
Yeah.
So basically, this is the behind the vertically that can. That's why you can use different patches to learn something like that. So how do you decide the size?
Yeah. So the question is, okay, how to decide the size of the patches? I think there are multiple things to consider. The first one is this thing needs to be computable somehow. So you choose just like a size that you can actually compute. So a Gaussian mixture model suffers from the curse of dimensionality. So if you choose the patches too large, then it's unclear whether this thing will actually converge. And maybe also like your distributions maybe has too many let's say multiple modes, for example. The second thing is that the size here relates actually to the size somehow of the PSF. So what you're interested in is, I mean, if the structures in the image are very large and much larger than the PSF, then this is not necessarily relevant for the deconvolution, right? So you're not necessarily interested in the correlation between this pixel here and this pixel in the image. So you're mostly interested in the local correlation. And what they found empirically somehow, I think, for example, astronomers typically use something like 5 pixels per sigma of the PSF, and this is just a bit larger. So this is the argument. So then this is used in the reconstruction of the image. So one can use this Gaussian mixture model then to build something like an approximate prior for the whole image. The way this works is you split your whole image again into patches. The authors of the computer vision paper found that like making those patches overlap is a good idea. And so this is something that I just used as well. And then for each of the patches, you evaluate the Gaussian mixture model and you find like which component is the most likely one. So this actually adapts to the structures in the image. And then for each of the patches, once you found the most likely one, you just sum up all the log likelihood values, and what you get is something like an approximate log likelihood value for the whole image.
So when you say the most likely one what? Component of the Gaussian mixture?
Yes, yeah, the most likely component of the Gaussian mixture.
I see, so you're only using one component.
I'm only using one component.
Oh, I didn't understand that.
Yes. So test-wise, what I've done is, and this I found interesting, I also just marginalized over the components. Just, I use all,
Oh, okay.
and then just sum up across the Gaussian mixture components. Just yielded effectively the same results. So it seems like there's one component that really dominates the value of the likelihood.
But it's continuous, which is kind of nice.
Yeah.
So that would probably change if patches were different size, right? Like, is a good approximation to just have one because they're small enough, you think, or?
That's a very good question. I mean, it might be related to the fact that indeed, for example, structures just cluster or seem to cluster. So there are edges, there are things like corners, and you find those again in other images. Maybe that's a fundamental property of image distributions or image statistics, like local. And this is how I get and then I change to the maximum a posteriori estimate. So I just optimize the whole thing with the posteriori to get an estimate for the images. Just a word on the implementation. And this is all implemented in Python. I gave it the name Jolideco for Joint Likelihood Deconvolution. The joint then actually refers to the slightly extended likelihood functions. So the likelihood here is now not only computed across a single observation, but it's computed across multiple observations. What's interesting here is that I can actually take into account different point spread functions for each of the observations. This is interesting, for example, for Chandra, where the point spread function varies from multiple or between different observations, or even if you decide to combine, for example, data from multiple instruments. I'll show that on that data set later. And then you have the prior distribution, and in practice you have this beta variable that is typically not used, but it's still good to have at some point, which quantifies somehow like what's your confidence in the prior. What I found interesting about this, so if you have this sum over multiple observations, this actually directly corresponds to the concept in machine learning of having multiple data examples, right? So concepts like stochastic gradient descent and mini-batch optimization directly apply to this, which I think is very interesting. The same for cross-validation and having training and validation errors. So these are then suddenly things that you can just do. Optionally, you can just reconstruct an upsampled image. So you can imagine that the image X now exists on a finite grid. Then you come up with the PSF and downsample, compare to the data again. And all this is implemented in PyTorch, and the code is publicly available and documentation as well. Okay, let me show a few examples on test data sets. So we come up with these toy data sets to test the algorithms. So there are scenarios A, B, C, and E. So scenario A just consists of grid of point sources that are bright in the upper part, they are green in the lower part, and they are like further or closer than again in the lower left. Then there's scenario B, which consists of point sources and an extended source here in the middle, and C at the edge. We see that okay, what's the edge what's the behavior at the edge of the algorithm. Then there's another scenario where there are point sources on top of a weak extended source, which is just a disk shape. And then there are these like structures, but the idea is to see whether there's some kind of preferred direction, for example, within the construction. And then there's this case of having some point sources and this file structure and this ring-like structure. These are just things that you find in astronomical images. Then we came up with two instrument scenarios. So the first one is called Chandra. So this is a rather good angular resolution, but lower effective area. So for the same observation time, you get fewer counts, but you have a better angular resolution. So this is what the data looks like after. And then we have a second scenario that's called XM. So this is like a worse angular resolution, but it has higher statistics, so there's more counts.
Do you add Poisson noise to that or not?
This,
Because those don't have any Poisson.
yeah, those that don't have Poisson, so this is just the expected or predicted counts that you get.
It's just a convolution by the PSF.
Yes, yeah.
But then in the model, you feed something with Poisson
Yes.
noise.
Yes, yeah.
And of course, there will be a higher relative Poisson noise for Chandra than for XM.
Exactly. Yes. Yeah. This is exactly what you get. So these are the results for the Chandra scenario. So these are the scenarios they want. So I forgot to mention this. So there are also like varying signal to noise ratios. So the scenario B actually exists like multiple source brightnesses here, the same for C and D. I'm just taking in this case A1, A3, C3, and A4. And then I've compared this with multiple other algorithms. So there's, I mean, those are represented by Jolideco again, but this is just a uniform prior. This basically corresponds to this Richardson-Lucy case, optimizing for 10 iterations and 1,000 iterations. Then there's a method called Pioneer. This is something that was developed in the Charles Statistics group like 15 years ago. This uses sampling and a custom multi-scale prior. It's a bit too complex to explain it in 3 words, but it's just like like a multi-scale prior. With this, and then there's the Jolideco algorithm with the patch prior that I talked about. This is this year. This one was learned on clean data, and then there's another patch prior. This is from Zoran Advice. This is the original computer vision paper, and this was learned on everyday images. Then if you apply this to point sources, what you can see is that so if you have this simple uniform prior, then you don't really get sharp images. If you optimize this to n, let's say, so with 1,000 iterations, then you get a good reconstruction of those point sources, very similar to Pioneer. And this is then here the case for the GLEAM and for the Zoran bias thing. So this is one interesting observation here, that the remaining extension in the point source here is a bit larger for the everyday image, because typically it does not contain point sources. I think this was the obvious explanation for this case. And then here in the lower right, of course, we can solve the sources and so on and more. Then once you have an extended source as well, it becomes a bit more tricky. So here you see again in this typical case of that the structures decompose if you don't have the prior information on the correlation. And this problem is then solved with the patch prior here. So actually these Gaussian sources, and compare just visually to the ground truth, and they have to look smooth again. While you still get a good reconstruction for the point sources, they are not as sharp as in this case here, but they keep or preserve the extended structures on the image. In a similar picture you have for the other cases here, where the structures decompose basically into a string of point sources in this case, and you cannot really be sure whether it was real or not. And this situation is much improved with the patch for them. The same holds for the underlying source here, or this really extended source. Here it decomposes only into point sources, and here it keeps the correlation structure. And then very similar again for this case here.
Sorry, another
Yeah.
question. So the thing of the single point, wouldn't it also have then if you're taking one Gaussian to image? How big are is 1 pixel or compasses? Like how many pixels are there that you put priors, the size of the pixels that you put priors?
This is, so the PSF for the Chandra case is, the sigma is 2 pixels of the PSF. And the remaining extension in those point sources here is maybe 3 by 3 pixels, something like this.
Would you not always be most likely to get an answer that is point source? Because of the Gaussian, because of choosing one Gaussian would look like a point source, right?
I'm not sure what you mean by this. So this, I mean, the remaining, yeah, this looks something, I mean, it leaves some extension in the point source, right? So otherwise you would expect really like a single bright pixel. So this would be the perfect reconstruction. And you get really close to this if you have the uniform prior, which assumes all pixels are uncorrelated. In this case, it would not be like, or like the right case, but in this is not perfect. And then the patch prior really introduces the correlation across the patches, and this then leaves the extended structure as you have it here. It leaves the correlation across the pixels and prevents that decomposers will do those single point sources.
Yeah.
I think this is like the technical explanation. You can take a more quantitative look at this using image metrics. So there's the thing called the structural similarity index and the normalized mean square error. And if you compare those across the methods, then so for the normalized mean, the lower is better. For the structural similarity index, like the closer it is to unity or to one, it is better. So the same situation as you have visually here reflects in those image metrics. However, I found, for example, in practice, this is a bit difficult. For example, the normalized mean squared error, you can find that two reconstructions can have a very similar value, but visually very different. And this was tried to solve with the structural similarity index, which takes a look at local structures and compares those. But then there's a bit of a problem again, because you basically average across a window function. And then the reconstructions again look very similar. I'm not even sure whether this is like
You're working in the Fourier space, because essentially, that's the whole point. You essentially try to do an ill-posing version. You add some essentially regularization to lift, the singularity. And essentially, what it looks to me like you're doing, you're essentially tweaking it in the Fourier space. So you're trying to essentially avoid it to become point-like, because that's what the natural deconvolution will be. If you push any deconvolution, it wants to give you a point-like solution. And you're essentially saying, no, I want in, a different part of Fourier space to get, to deconvolve that, because you prior say, I know that the solution is smoother than just a bunch of points. Except that once you put that, and your solution is really a bunch of points, then you're gonna blur them. Because you're assuming that they're not points.
Yeah,
See, that's essentially the fundamental problem of any of those deconvolutions.
Yes, yeah, but the point is to find a compromise between all those.
Correct. So
and this is what we've tried to show here, right?
No, I understand, but if you would actually do, normalized means in the Fourier space, you could see how is different the solution in high spatial frequency versus low spatial frequency.
Yeah, I agree. This would be good perspective to add. I mean, right now, I think I'm not aware of image metrics in Fourier space, but they must exist. Then we compared across multiple varying background levels. So we assumed 3 levels of background with 0.1 count per pixels, 0.1, so increasing by a factor of 10 and 1 count per pixel. This is just the D1 scenario. There's nothing really surprising here. So the quality of the reconstructions improved as you have more signal to noise. There are some things, so this is really like a very, very weak signal. It can barely reconstruct this. This is expected. I mean, you can barely see that there's something. I mean, it slightly improves the signal to noise ratio. I mean, of course, the point sources are reconstructed and they're right there. We can see that probably there's some kind of structure you need to get some of it. It's maybe there. But it's not all too surprising. Of course, for low signal to noise, there's less sharpening. And then for extremely high signal to noise, so this is the case here, it seems to converge to the ground truth. But we have not really verified this, but just like by the more interesting case is the one with the varying instrument scenarios. So this is just using the Chandra data set, SFTX and M1. And this column here uses the joint reconstruction, so really combining the data. And you can now visually just compare. So this is just the final reconstruction, so you get good point sources, you find the structure here in the spiral arms. And it gets more pronounced as you have higher signature noise ratio, obviously. Interestingly, this also happens for the XMM case. So this is not necessarily a saturation effect. So the spiral structure is really very visible, but interesting to roughly reconstruct. This I found a little bit surprising. But the most interesting effect that we found is following here, that we really get the best reconstruction once you combine the data. So what we found here is that including the lower quality data in terms of angular resolution of XMM actually also improves the result. So with Chandra, you still have this effect that sometimes those things will decompose into point sources. And then once you add the XMM data, this introduces the correlation across pixels to further distance. You actually get rid of those things. So the XMM data actually tells you that there's a correlation between this pixel and this pixel because of the underlying resolution.
So in this slide, I have the previous one, it looks like maybe it's this visual. It looks like it's kind of a bimodality with point sources. They're like sometimes it very sharpens them up, and sometimes they.
That's
they want. Can you explain that?
Yeah, that's an effect that we've also found, and we don't. So what you're referring to is the following, right? So sometimes the point sources pop out, let's say, so they get like really sharp here, and sometimes they don't. Right? So they keep me, or they're saying like this. I have no good explanation.
Did you try to run multiple realization? Because my guess has to do with the Poisson noises. Because the Poisson noise essentially won't fly statistically. It has no, spatial structure. And so when you have a lot of Poisson noise, it will be very difficult to pull out a point like underlying source. Yeah. If your Poisson noise is randomly more spread, it will not give the impression. So that's where, my guess is this is a single realization. You're not run 100 cases where you're essentially
this is for
100 different kind of Poisson noise.
I'm using 5 observations.
Okay.
But it's not 100. Yeah, this would be a good thing to verify, I guess. This is, here you can see it. The effect goes away once you have high signature noise, so I think your explanation is very plausible. This is then an example applied to real Chandra data. So this is supernova remnant called E0102. This is the whole observation. This consists of 25 observations of Chandra. And I've run the deconvolution algorithm on this using a path prior learned from this JWST class A image. That's 270 arbitrary choice, but it made sense in this case. And you can see that the image is denoised and it's sharpened. And you can take a look at those zoom images here. So this is some filament structure. And what's interesting is here that the correlation across or along the filament is actually preserved while it's sharpened perpendicular to it. Then here's some source where people claim this might be the compact object of the thing. It's very visible in the data here, but it really pops out here in the zoom image. What I'm doing in this case, in addition, is that I actually have a model for the background. And this is optimized along. So what model means in this case is just a constant. So there's no complex background shape here, but this is modeled along with the data. So the norm of the background can actually vary. And this probably gets rid of some background emission. Here. And here's another case for a circular filament or like more complex structure that we look sharply into. You see that there's some hydrodynamical structure, possibly something like this.
Do you expect to evaluate sort of error bars on that or likelihood?
That's a very nice question. This is something that is, so the interesting part is that this could be done. And right now I have not done it, but it would be nice, for example, to change to sampling from the posterior, for example, but then you would get the average. But right now, this is not something that I've used. Here, one application example.
So you can also take your reconstructed image,
Yeah,
convolve it with your PSF,
Yeah,
throw some Poisson noise, run a causal realization, see how you reconstruct it,
This is,
and that will give you a distribution of all likelihood what your reconstructed is.
yeah, this is done with bootstrapping, and this is exactly something that we've done for this example. So this is just the same example region that I've shown before, and the question was, so if you consider like a real physical measurement, the question is whether there's some extension in this filament here. And the answer here in this case then would be yes. So here we've computed the profile of the count, so it's shown with the noisy curve here. And then we've computed the same profile on the deconvolved and denoised image, and this is shown with the violet dash curve here. And then we've computed the full width maximum and compared. The deconvolution shows the property is much smaller than 30%, that you just measure on the bare counts. And then from the bootstrapping, you also get an error associated to this. You can also do in back of an envelope computation, what you would actually expect in this case. So you roughly know what the size of the Chandra PSF is. And then you expect, if you assume that everything is Gaussian, you just expect the usual relation that the variance is just add up, and you can get a guess. For this, the guess in this case is here that the intrinsic width of the thing would be roughly 0.5 arc seconds, and what we get is like 0.58. So it's slightly larger, so the deconvolution is not perfect, but you still would conclude in this case the extension that defines is real. Here's another example applied to Fermi LAT data. So this is for another runner called Vela Junior. So this is what the data from Fermi LAT looks like. So it's really these bars. In this case, there are not multiple observations, but this is just integrated the whole exposure of the Fermi LAT, like more than 10 years, definitely. But the joint likelihood in this case goes across multiple PSF classes. So Fermi LAT has the concept of having multiple or having different reconstruction quality for the events. And those are associated with different instrument response functions on PSF. In this case, you can actually compute then the likelihood across multiple of those PSF classes. And this is the result that you get in this case. This is what the residual looks like. So you can get flat residuals, whatever that means. I think the physical interpretation then of this is left, of course, to the people that do the convolution. The features that you find here roughly line up like with data from other instruments. So here's the image from the James Webb Telescope, about 1 TeV. Here's the image. And here's the Fermi TS map. So this is the kind of quantity that typically is shown. And you can see that it is the angular resolution is slightly better, and those it's less noisy, and the features that you have roughly line up. But in any case, I mean, if you're interested as a science user in a certain feature, then you should do like more, or should test more of that and make sure that the feature that you're looking at is actually real. So yeah.
No, maybe I'm understanding completely, but you show that some cases where you have certain number of iterations. In this particular case, how do you decide when?
Yes, yeah, that's a very good question, and I have not mentioned this. What I do in practice here is, so the algorithm runs or is implemented in PyTorch. It runs on the GPU, so it's rather fast. So for this Chandra image that I've shown, this is 1,000 by 1,000 pixels, and on the GPU this runs roughly in 15 minutes, something like this. And what I did was I tracked the loss and just made sure that I'm like at the far end of the convergence. So what you typically see is like this shaped curve, right? So, and I just made sure that I'm somewhere at the far end of the optimization. So I've wasted some computation time in order to be sure that I can reach.
So you essentially over-iterate. You just iterate by a large number.
Yes.
So that the number of iteration is irrelevant. There's a very large number.
It's just a very large number.
Which one is essentially the metric of the loss? That's flat enough.
But I thought maybe I'm remembering when you iterate more, it looks like a little bit more pointy.
This is the case if you don't have a prior. This is the case for the uniform prior, where it looks more pointy, and
the whole point is once you add the priors, is not
exactly
not to iterate to almost full
exactly
right solutions.
Exactly, yeah. And then this need for tracking, like, okay, how long duration iterate this does again. You can just say like you optimize it to end, just basically. So there's, I mean, typically what you could do, I mean, this is also what I mentioned here. You could work with, if you have enough data, you could work with an independent validation data set, right? So you could evaluate on your validation, and then you would stop once your validation loss gets down. So this is, for example, reasonable for certain sources that you observe with Chandra, which is like enough observations. You could do something similar for Fermi as well, just by splitting the events and splitting into multiple time intervals, and then you would also get like multiple observations, but in general, it's just like much fewer data. So this is.
So does it bother you that the Fermi TS map looks rather different, like around 2 o'clock on your clock dial there? Fermi TS map is at its brightest almost, yeah.
This region.
Yeah.
I have not really double checked this in general. I mean, for TS map, you would expect that this is less smooth, right? Or it's even more smooth because like, you run this TS kernel. So what you do for a TS map, just in case you're not aware of this, so you take the PSF and at each pixel you fit the amplitude of the PSF. And then you compute what's the significance of a point source at this given pixel. And what you end up again is like a smooth version somehow of your data. And so I'm not surprised that the things are larger here, but indeed I agree. I mean, in this case, it looks different.
And are the observations taken at the same time? Could the difference be that the source is not the same at those different times?
This is something to mention here. So if you take a look, for example, at the Hess map here, so there's an pulsar. So this is the green star, and there's clearly emission in about 1 TeV that is then probably not present here in the 2D case. This would point in this case, oh, it's maybe a different object, or probably different.
Those are not for your observations. So
Yeah.
you have to, you're making the assumption that the underlying source has not changed at the 2 different times that
Yes.
have been observed. So you have to be careful with that.
Yes.
True,
Yeah.
but I mean, if it's a Fermi map and a Fermi map, it can still be different time periods or different energy ranges or whatever.
This could be. I mean, for sure, this is not the exact same data that was used for this.
Okay, there actually be something interesting, the fact that they're different. If they both are true.
Yeah, I would never claim in this case, for example, that all the features that you see here, you should trust them. But it gives you, I think, as a science user, it's a good way of taking a look at the data because it gives you some ideas that you probably might have not gotten otherwise. That's it. For example, those. So here's the summary with some further ideas. So Jolideco is a method for joint likelihood deconvolution for astronomical images with Poisson noise. It uses this patch-based image bias to reconstruct the flux image. And it can really combine the data, taking the corresponding instrument response functions for the observations and the different instruments into account. We found that both the patch prior as well as accounting for multiple observations and multiple instruments really improves the reconstruction quality. Then things to work on in the future. So currently this uses a maximum posteriori approach. It would be really nice to change this to posterior sampling, for example, then to get a quantification of the associated errors of the reconstruction. Would be interesting to extend this actually to the spectral dimension. So, for example, with Fermi, the point split function actually varies a lot with energy. So this would be interesting to have. And also, it would be interesting to, this has been shown in literature that this technically partly works to handle, for example, multiple flux components. If you have in an image an extended source and known point sources, then you can add this as prior information as well. You can just put in the point sources and then reconstruct the extended source using the Jolideco method. And finally, there are some ideas like one could try different approaches for the patch modeling, things like normalizing flows, like other mixture models, student distributions, etc. Yeah, thank you very much.
We've been interrupting all the time. So
Yeah, that was great.
Any more questions or comments, or we have some time for?
We have one from online.
Oh.
Yes, hi. I just wanted to ask a standard problem in SED fitting is PSF matching across different wave bands. So you can have Wise, Spitzer, Swift, HST, etc., etc. So the standard approach is to convolve everything to the worst PSF, which can be a disaster, or to leave some wave bands out. And there are some tessellation programs like AFIT, TFIT, and all sorts of things. I'm wondering if you can extend what you presented here to offer some approach to that. One has to be careful, of course, because the problem is that some features may just not be present in different bands, but maybe some progress can be made.
Yeah, thank you very much. I think that's in general interesting idea. So the assumption for this algorithm here is that the underlying flux is the same. And this does not necessarily, this typically does not apply across the energy domain, right? So the morphology and the flux will actually change with energy. And this is then something that could only be roughly tackled like in this scenario where you take into account the spectral dimension. But then you have some need of actually putting a prior on the spectrum. And this is very complex again. Like, I mean, in X-ray also, like the spectra are very, very complex. So my immediate response to this would be that the method is probably not necessarily suited for exactly this case where you propose. It's mostly also image-based. And I think I mean, you mentioned that the data is smoothed to the worst PSF. I mean, for points, for example, there are more clever things to do, I guess, right? Because you can really just correct, for example, for the containment of the PSF. But I think this Jolideco method would not be my first choice, I think, to check on that part.
Thank you.
So I don't know if this is getting into the nitty gritty too much, but I am curious about the leading eigenvectors of all the covariance matrices and how redundant they are. And so there's probably some metric of redundancy, like inverse covariance of one times the square root of the other on each side, or something that is equivalent to taking many draws from one and asking what their chi-square would be with respect to the other and things like that. Like there are ways of just asking, are these covariance matrices kind of redundant? Because to the extent they're redundant, then what you have is n means, and you're basically choose a mean. But if the covariances really contain interesting information, then one wants to kind of know how many eigenvectors worth of information is it, and how. I don't know. It just. Because I could imagine that then informs the decision of how many Gaussians do I use, how many patch do I use, and so on.
Yes, I mean, I think this is probably also relevant for the performance. I mean, you could just like simplify the evaluation of the Gaussian mixture model. As I said, like in the original publication, this is at least visually shown, like what those look like. My guess is also, they're probably redundant. To a certain degree, one just not cares. You just say like, okay, this is in the actual information, and it just uses the patch prior or this distribution just as a model for the prior distribution, whatever it looks like. But there's probably interesting information in these things.
Yeah, clearly the technique can work without understanding all that. Yeah. Just as I want to know what a neural net has learned by playing with feature visualization or adversarial inputs or whatever, I kind of want to know what this has learned.
Yeah, we can take a look at this example just after. Yeah.
Do you see opportunities or kind of what level of interaction do you see between this kind of work? And so radio astronomy, things are a little bit different, like talking about Poisson noise.
Yeah.
We're working for the native data or in a 4D space pretty much. But there's like a ton of overlap, but they're also very different communities. So I guess, do you see ways to take advantage of the overlaps?
This method was pretty much inspired from radio astronomy. Right? So this patch prior approach, as I said, was then used for EHT imaging, for example. So it was shown to work, let's say. But then to apply this indeed to X-rays, then you have to modify the algorithm, take into account the Poisson, the Poisson statistics and these kind of things. But in general, I think the overlap is indeed in the image processing or computer vision part. And this is, I think, very interesting, for sure. I think like, because there you can bridge the communities. It's just probably, I mean, this is also what like this, I guess what you're trying to achieve with the AstroAI community here as well, right? Is bridging the communities and say, okay, where are the common things that we have in methods, and then exchange and learn from each other. And there, I would argue for this method, I was inspired a lot by radio astronomy. Like, there, the deconvolution is a need because otherwise you get like not any, or almost not any image at all, I would say. It's less of a need for X-ray and gamma ray astronomy, but I think I've shown that at least that you have this advantage of combining the instruments. You can really maximize your scientific output by having more data available to analyze.
Okay, if there's nothing, if you have more questions or discussion, we can talk about it over lunch because we're at the hour. Unless there's something online on Zoom, any questions? I think we can continue. Okay, well, let's say thank you.